Okay, so this is going to be a really basic intro to LTSpice and kind of the things you can do with it. It's not going to be super complicated because, to be honest, for undergrad you don't really need to get that complicated with LTSpice. It can actually do a lot more than what I'm going to show you, but this will cover pretty much everything you're going to need, at least up until senior design. So if you've never used LTSpice before, I am going to start like at the very basic level, like even just how to place components. If you have used it before, probably the first half of this will seem kind of redundant to you because it's very simple. But let's just go from the beginning here. So once you have LTSpice open, if you want to start creating, you click on this little button for a new schematic.
Could you show me again? I didn't see that.
Right up here in the left-hand corner, it looks like a play button.
Oh, yeah.
Yep, new schematic right there. And then you'll see you've got a whole bunch of options up here at the top. And remember the first time I used this, like I saw all of these up here, and it's like, okay, so obviously this one's for a resistor, this one's a capacitor, this one's an inductor, but I had never messed with diodes before, so I didn't know what this was. And I definitely thought that this, the one labeled for components, was just going to be like AND gates and NAND gates, like Comp E270. But it turns out that this one specifically is a lot more than that. This is where you're going to get all of your voltage sources, your current sources, your op amps. There's actually a lot in this component dropdown. But let's start off much more simple than that. We're just going to make like a really basic RC circuit. So what I like to do when I'm making circuits is just sort of think about all the components I'm going to need and then worry about making the circuit pretty later. So for an RC circuit, we're going to need a resistor. Oops, don't scroll all the way down. Let's zoom out so that if it scrolls, so you can zoom out with the mouse wheel. Right click gets rid of the component you were just holding, so now you can come here, grab your capacitor, we'll need that too. And we're going to need a voltage source, and like I said, voltage sources are actually in components right here. So you'll open that up, and then in this search, you'll just type in volt, or voltage if you wanted to. I wonder if you can just get there with just VO. Yeah, if you just type VO, you can get that voltage source too. Throw that off to the side somewhere. Now, so if you want to, you can try to set this circuit up with all of your components facing the same way, and wherever you just drop them. But if you want to clean it up a little bit, you use this move right here, up at the top bar. Start grabbing things, move them around. And I'll show you what drag does too in a second, because that one's actually pretty cool. So let's say we want to connect this over here. Want to go through the capacitor, come down here, go back into the voltage. So we're going to need a ground here, because right now our circuit the electrons won't go anywhere. If we tried to simulate this, it's going to say that it's not grounded. So this is your little grounding button, and you can just stick that right on the wire. If you don't like the way that looks, just give yourself some more wire. Then you can grab this guy and move him back over here. Now this is the move button, but you can also have a drag button. And this means that, so with move, it would just be taking the component out, but with drag, it'll actually take the component and the leads with it. So that can be super useful if you don't want to disconnect everything and put it all back together. So if I wanted to, I could just move this all the way around over here. I could say that I want my ground to go down here now, whatever I want to do. But now, see the way my resistor is, if I was going to try to attach this to my circuit, now it's in parallel with my capacitor, so I don't want that. I want it to be in series. So you'll select your move button, pick that up, and hit Control R to rotate it. Now you can just snap it in here like that, and it'll automatically delete those traces. Or you could have, instead of doing that, just taken the section of the traces out right away. But unnecessary, because it'll do that for you. So let's put that in there. Okay. So now we could try to simulate it, but it's going to ask us for component values as soon as we say, like, okay, stop time 5 seconds. Okay. So it's going to say that it can't find any of the values for our components, and then give us a bunch of errors. So let's say we want this to be 5 volts. We'll have this capacitance be 0.1 micro. So for most of these, the values will work exactly as you expect. U is micro, except for M. Now you would think that this is saying 0.1 meg, but this is actually saying milli. To get meg, you would have to actually type meg. It's a little confusing at first, but you kind of get used to it. Either way, we're not...
Jason?
Oh, what's up?
I thought something was going to pop up. We actually can only see LTSpice. The pop-out windows don't show.
Oh. Okay.
If you know how you click to stream your screen.
Yeah.
And it you have your applications option. You can stream your whole screen because there's a tab up there. It's application on the screen right next to it.
Here, let's see if I can get that figured out.
Yeah, you're gonna need to close the stream and start it.
Okay, hang on. Is that working? If I actually... Can you see that pop-out window or no?
No, okay, so what you have to do is you have to share your whole screen.
Yeah.
Okay, so you know how you click share your screen and you have the whole pop-out and it has, applications, and there's a tab there.
Oh,
right
I see
next
it,
to
I see it.
applications, it's a screen.
Yep, got it. Now you can see that pop-out, right?
Yeah.
Alright. Sorry about that. I assure you this looked pretty much the same for the capacitor as the resistor. Actually, let's make that 10K. Okay. So this is what I was talking about, this U right here. Make that an M. Capital M is for milli. Meg is for mega. So that's a bit weird, but it is what it is. Oh. Micro. Okay. But let's do some actual simulating here. So, if you go up here to simulate and you go to edit simulation command in this drop-down, this is really where you're going to get into what you're trying to do. So, if you leave no units on this, it's going to automatically do seconds. For most of your circuits, they're going to reach stability long before 5 seconds. I usually just do 3 seconds, and that shows you a lot of your stability, as well as how long it takes to get there. You could also tell it to stop simulating if steady state is detected. Sometimes that can be really, really useful, but if you're using custom components like you will for 330 and 430, where you're going to have to insert your own BJTs and MOSFETs, it won't be able to do this steady state detection. So just leave it at 3 stop time for now for transient analysis, and it'll down here tell you that you're doing a transient that'll stop at 3 seconds with 5 volts. So now you can simulate, and at first it won't show you anything, so you have to start clicking on stuff down here. Let's zoom in on that guy so it's easier to see. So you have a bunch of traces. Now this probe is for voltage, and when it turns to a little ammeter, that's looking at current, and it'll tell you which part of the component you're looking at and what it can record from there. So say you wanted to see the voltage coming out being fed into the circuit. Well, okay, it's 5 volts like I told it to be. But what's the voltage on the other side of the resistor? Okay, so it's also 5 volts. You can check your voltage here. So this basic circuit's not really doing much, but you can see that your current is pretty different by clicking on the current through the resistor. Same with the current through the capacitor. You can see that they're actually opposite, which is kind of what you would expect for a capacitor and a resistor. Now we got a whole bunch of traces here, and maybe we saw something that was a little confusing and we just wanted to see capacitor current. So if you want to get rid of traces, you could just go up here and hit delete trace. Or you could select the whole window and just hit delete, and it'll give you these scissors, and you can just go through and say, okay, I don't want to see the current in the resistor, and I don't care about the voltage. So now all you can see is the capacitor current. Now there's also some pretty cool stuff you can do. Once your circuits get more complicated, this will be really useful. You can actually start naming your nets. And if you want to, you could say that you have like a Vout net. Okay. And you can put that tag right there on your circuit. And you can say run simulation again. And now you can specifically use Vout for measurements, and see, it'll even tell you that you're looking at your Vout net. And if I hold Alt and left click on Vout, it'll highlight everything that that net is taking into account. Now, since this circuit is really simple, like that's a very easy node to look at. Like 210 would cover this for you. But once your circuits get a lot more complicated, if you have wires that are crossing, you just have a lot going on, it can be really helpful to highlight what net you're actually looking at and which components it's taking into account when it takes this measurement. So I'm gonna open a different file up real quick. So these are just a bunch of things that I put together. Here, let's open this one up. So this one is almost the exact same circuit, except it's using a pulse on the voltage, which you can set up yourself. So previously it would have just had none, and you would just put the DC value in. But if you go to pulse, and it tells you right here, so you're going to have an initial voltage of 0, which means your pulse starts at 0. When it turns on, it's supplying 5 volts with no delay. You could set this delay. Let's set that delay to 10 milliseconds. Rise time, so this is how long it takes to go from 0 to 5. This is how long it takes to go from 5 to 0. This is when it turns on. This is how long each period is, and this is how many cycles it's going to pulse for. So now if I run this and, oh, don't need that one anymore. And I look at the voltage coming out of this, we can see the pulses right here. These are our 5 pulses, which is good. And you can actually see right here that tiny little bit of delay, or the tiny little rise time that it has in it. Oh, if it's not clear how I'm zooming in, you're literally just going to open this up. If you click this button, it goes back to the standard screen, this zoom full extents. But if you want to zoom in, you just click the zoom in button, and then you can drag to zoom in. Just drag a box. And that can be tricky when you have very small signals with super tiny ripples or even huge ripples. So you may have to like zoom and play with your limits just to see things. Like if I make this box really long, it can zoom in on just the top. Let's open something a little more interesting to look at. Okay, so if you've already taken...
Wait, Jason, can you explain what each number in that pulse thing means? Because I assume it's low, high, active time, rise time, fall time.
You're talking
three numbers
about
I don't
in this one, right?
Yep.
Yeah, okay. So if I open this back up, so it actually kind of explains it right here in this pop-up window. You can see that, right?
What's T on?
When the voltage actually turns on.
Oh, okay. Period. Oh, okay.
So if one of these, the way that I learned this is if one of them doesn't quite make sense to you, just like change it to some ridiculous number. Let's just make it like 100 milli. And then simulate it again. Let's get rid of this for now because we don't need that. Let's make this a little bigger. Okay. So we've made it 100 milli, and now we can see, you see how we've got this weird bar up here now?
Mm-hmm.
So it's making it so that it's on for longer than the period of the pulse. So it has a pulse, but it also has a period where it's just on anyway. Oops. So you don't want that. You want your T on to be at least less than your pulse. Let me look through my notes real quick and see. Okay, so I'm going to open up a more interesting circuit real quick. So this one, instead of DC voltage, it's got a sine wave here. And I can show you that all you have to do is select sine, and then you get a DC offset, which normally you're not going to have to worry about unless you're told to have a DC offset or you really, really want to. But you can see that our amplitude for this one is 10 volts, frequency is 50 hertz. So if we want to look at what that looks like, oh yeah, I forgot when I designed this, I actually used my own model of diodes, and I can show you guys how to do that. Actually, I'll just show you that right now. So when you want to make your own diodes, what you have to do is go into your LTSpice folders. So my LTSpice folders are in this drive. They're going to be wherever you saved wherever you installed LTSpice. So mine is in program files. And I know you guys can't see what I'm doing right now, but hopefully you all know how to get to program files. So here, I'll wiggle that over there. So now you can see it. So you go to LTSpice, and then if you go to libraries here, and then components, you can see this standard library. It's a BJT file. You open that up, and these are all of your, so this is like a, you can see that this model 2N44, this is a PNP transistor. And then these are all of your transistor characteristics. So if you were to go on like DigiKey or something like that, you could actually look all these characteristics up and just make a new transistor model if you wanted to. So I remember when I was replacing these, all I did was I copied one of them, Control C, give myself a little space, Control V, make a new one, and just immediately changed the name to Conan's. Now, all I've done right here is make an exact copy of that transistor, that 2N5087, and renamed it my own. But if I changed any of these values in here, like I could change the forward voltage, I could change the series resistance, I could change all kinds of stuff about it and probably break it and make it never work again. But, you know, usually you don't want to do that. Usually you want to make things that make sense or just copy one from DigiKey. But even without the parameters properly installed, you can still simulate it. It'll just say that it's going to continue with a default diode, which is okay. It's just not going to do exactly what I had planned. But you can see this is actually still pretty close. The peak current is right here. So it's got a peak current. Let's say we wanted to see what that exact peak current was. So we want to attach some cursors to this, and I always just do first and second, and it'll pop them both up in the same place. So you'll grab one, you can move it around. So let's put it right at that top. So we can see here that the peak current through diode 1 here is about 340 milliamps, which isn't too bad. But we could also see how long one of these waves is by moving both of those. Now if you wanted this to be more exact, you could say to put cursor 1 at microamps. Let's put cursor 1 at 0 microamps and see what happens. Oh, we can't go down to 0. Can we go to 1? No, it won't let us change it anyway. Oh, give me back my cursors. We can still do it like this. So we can see that the distance between the two is here. So we have 8.9-ish milliseconds. Yeah, so this one's actually a pretty low frequency. If you were to feed this into a speaker, you'd be able to hear it. It'd be pretty hard though. This is like 100 hertz is about as low as you could hear. Let's look at more. Oh, okay. So this is a good one. Let's say you wanted to see how much power was being dissipated. So we already know that if we're running the simulation, we can see voltage when our little probe is like this. If we hold it, we can see differential voltage. So we can see voltage between nodes 1 and 2. So this is node 1, this is node 2 over here. We can see that this is what our differential voltage looks like. So it's being boosted and then held steady right here. But I could also look at how much power is being dissipated by holding Alt. If you hold left Alt and click on this, you can see how much power is dissipated across this resistor. So it's about 81 megawatt, or 81 milliwatts, not mega. Now if you wanted to see just the average, you could control and left click. Where'd my average go? Where's my average?
Rip. Oh, it worked.
Right, so control and left click is going to give you your average.
Will it though?
It will.
Are you sure?
Yeah.
Wait, so is it the root mean square sort of average?
No, it's just going to give you
like...
just like the peak to peak. Once it stabilizes, it'll show you what the average was. Which is useful if you don't want to calculate it by hand, but you definitely could. I know that I did all of 330 and 430 not knowing that you could just left click and get the average. Calculated them all by hand.
Every single one.
Yep.
Feels bad.
Okay. So I had a little project in mind because what I wanted to be able to do was make a really simple circuit in Spice and then show you guys later how to take that circuit and put it into something like KiCad, and then actually have that printed out at SDSU and then put it together. So what I ended up coming up with is how to blink an LED. So this is what I made last night. And what's cool about this is that I've done one thing that'll come in handy for you guys later, once you have multiple inputs, is you can just take your voltage source and detach it like this. So you can have this guy and you can put it anywhere. You could shove it way off to the side. But as long as you have these nets here, that voltage is...
How did you do that?
I'm about to show you. It's very exciting.
Show me now.
Let's get rid of those nets. Okay. So the way you would have normally done this is you'd have this guy, he'd be over here, and he'd have a wire going from here to here to here. And this ground would go away. And you'd have him attached here to here. And it's like, okay, like that's cool and all, but I don't want these traces here. They're ugly, they're annoying, I already know they exist. Let's get rid of them. And let's go to our tags. And we're gonna say, to make a port type, we're gonna say make an output. And we're just gonna call this V1, because it's voltage source 1. Actually, let's change its name to VDD. So you'll say that VDD is coming out of the positive terminal on this voltage source, and then you'll go up and you'll make another net and you'll make it an input, and you'll also call that VDD. So now these two tags are an output and an input, and you'll say, okay, I want the input to go right there. Cool. So now, no matter where this voltage source is on your schematic, it's always going to be feeding this net that it's associated with. Which for this schematic isn't super important, but it is nice later because you'll have stuff with like 3 or 4 voltage sources and like 2 constant current sources, and it's nice to just have them all side by side so you can really quickly click on whatever you need to see when you're simulating the circuit. Now I've also gone and made nets. Go away, that one.
I have a question.
Yes, sir.
So what if you did a current net, like you had a current going into one node?
Mm-hmm.
Or basically what happens if you try and drive a node to 2 different currents or voltages or something like that? Like, actually no, they'd add and subtract. Never mind. I'm just being stupid.
I mean, it's a good question, but yeah, it sounds like you're on track. If you're pushing,
like if you here's what I see. Like you know the V1.
Yeah.
Where you have your ground, your 6-volt rise, and then like if you had one right next to it,
mm-hmm.
there was another 6-volt. Like basically 2 batteries in parallel.
Mm-hmm.
Yeah, they would just add, right?
Yeah.
Okay, cool.
So let's look at. I made some nets here just to show what's important about these BJTs. If you haven't learned about BJTs yet, like don't really worry about this. It's just cool things to look at. So you can see this sawtooth that's being generated by the BJT as its gate is being saturated. Same with this one. You can go look at this one, so you can see it's getting like a little tiny pulse. As soon as Q2 saturates, it pulses into Q1 and then drops all of the current. And then Q2 has to recharge to saturate again. But the interesting thing about this is that when Q1 has this pulse right here, it goes directly to the LED, and that's how you get this LED to flash. See, the current that goes through the LED happens when Q1 pulses like that. So this circuit, without any kind of like integrated circuit or timers or programming or anything like that, this circuit will pulse an LED. You can get it to flash. Now, so if you've taken like Comp 375, you know, I mean, it's not a lot of work, but it is more complicated than just plugging something in to get an LED to blink. But this one does it without any programming. This is just straight up analog devices that just make an LED pulse, which I thought was pretty cool. So I think for our next workshop, I'm going to show you guys how to actually make this in KiCad, and then we would be able to print it out and you could actually build it and have a little blinking circuit board if you wanted. But let's talk about how we actually named these components, because that's important. So once you put your BJTs down or your diodes or anything like that, you can right click them and you can say like pick a new transistor, and this gives you, you might recognize these, like this 2N5087. That's the one that I had copied to make a new transistor in. So this is from all of your libraries, and you can extend this way out to see all of the parameters of these BJTs. For the most part, they're not going to be super important to you. There's like a handful of things in here. I'm trying to find one. This VCEO is important. VAF. Those are the only things you're really going to be looking for. But let's say we want to change this to 2N5771. I have no idea what that does or why it's important, but whatever. Now this one, I do know that if you go to the lab, we have a whole bunch of these 2N2222s. So let's change to that. Let's run it again and see what this changed about our circuit.
I do have a quick question.
For sure.
So you kind of just look at, do you like know? Sorry, do you like know what those components are or do before? Because I can't really read it, the list, so I don't know what information is given on that when you're picking that huge list of different components.
Right. So normally, what you'll do, you'll be given an assignment, or you'll be trying to design something on your own, and you'll say, okay, so I want a BJT that operates on 6 volts and can handle 500 milliamps of current, something like that. And then you would just hop on DigiKey and just put those filters in. And I'll show you.
I'm trying to find the name. Yeah, I've seen DigiKey, me and Jason.
Yeah, I'll show you more about actually choosing those components when we do KiCad, because it'll become really important, because you'll start to care about their size and their foot pads and all of that kind of stuff. As far as LTSpice is concerned, you really only care, one, that you already have a component selected. So you've already been prototyping, you already know what you're going to put in your circuit and you just want to simulate it, or you've been given an assignment that told you to use a specific transistor or diode or something. Like I think in 330, Professor Tay used to tell us to use these 2N2222s. So you would just select those and just move on with your life. This
I don't want to move on.
Well, if you don't want to, I guess you can just not complete your project.
Damn.
Yeah. Let's see. Oh, this is a good one. This will come in handy for you in 330 and 430 if you haven't taken them yet. You can go to View, and you can tell it to generate your bill of materials for you. It's not going to be too exciting right now because we don't have that many parts in here, only 5. But once you have, like, you know, crazy circuits going on, it's nice to know how many of each thing you actually have in there that you would have to purchase. And it'll also give you a printout of all your part numbers and everything.
Okay.
But that's actually kind of it for the super basic stuff. Like, I can show you guys some more circuits, but like, I guess I could show you... Where's one that's fun? Oh, this one's fun. Oh, if you wanted to add comments and things...
Oh, yeah, carry on.
Yeah, you got your class to go to?
10 minutes ago, yeah.
Yeah. Go away, Ethan. Go to class.
No, I don't wanna.
Anyway, well, this is your little text box for adding comments. I only add comments when I'm working in a group, though, and I have to, you know, leave a message for somebody. But yeah. So do either of you who are left over have any questions? Or do you want me to show you how to do something? Hopefully I actually know how to do it.
No, I don't have any questions at this point. Thank you very much.
Yeah, so if you want to, I think in about 2 weeks, I'm going to do a KiCad class, and I'm actually going to take this blinking LED right here, and I'm going to add a button to it so that it's not always on. It'll only be on when you want it to be. And then we'll actually get this thing on a PCB so that you could print it at the school and put it together. But that'll be later. That'll be in about 2 weeks.
Yeah, it sounds great.
Elise, did you already know all of this?
Not all of it. Like, I did actually learn some things. So, very neat. Thank you very much.
You're welcome. All right, well, thanks for coming, you guys.
Yep, thank you.